Good day everyone, I am Engineer Mark, your Technical Support Engineer from MIDAS IT Philippines. And today, in this short webinar, I will be discussing more on the floor vibration analysis and time history plot due to pedestrian load in MIDAS Gen. So these are the contents of our study for today. So for those of you who haven't known MIDAS Gen yet, MIDAS Gen, we call it one-stop solution for building and general structure because as you can see, you can design your building, your plant structures, spatial structures, as well as the specialty structures. For the advanced features of MIDAS Gen, you can do detail analysis, heat of hydration analysis, post-tension analysis, and of course, the construction stage analysis. If you study more or explore more about our software, MIDAS Gen, you can see that there are lots of advanced features that you can only find here in MIDAS. So for the GUI of MIDAS Gen, so as you can see, you can find the ribbon menu, the toolbars or the shortcut keys for this ribbon menu. You can also find here the task pane, the table window, the status bar. You also have the context menu, the command line and message window. So this command line and message window is same with the CAD software that we are familiar with. We also have this works tree. The works tree shows the information on the structure. So to begin with, let us discuss some of the importance of floor vibration analysis in our structure. So an example of this will be the human activity which causes the vibration of structural system is a significant serviceability design consideration. So it is also very important that the structural system protects the occupants and or other sensitive equipments from excessive vibration, just like in the hospital. So when resonance occurs due to this vibration, this may pose a major problem not only on the property but also to the lives of many. So I will be discussing resonance later or the meaning of resonance for those who are not familiar with. So the continuous vibration on a structure will also make the structural members experience fatigue, thus may cause failure, especially for steel structure connections. So human comfort should also be considered in our design. So these are some that I can cite regarding the importance of floor vibration in our design. But of course, I know you have lots of ideas. What are the floor vibration can impose into our structure? So it has this major, it has these different results, especially if we do not consider this into our structure. So for the theories and terminologies in structural vibration. So here I will not delve deep more on the structural dynamics, only on the basic concept. But I can suggest you can read some of the text regarding structural dynamics like the structural dynamics of Chopra and Maria Paz and so on. So here, natural frequency. So natural frequency, it is the back and forth motion at a definite cycle per unit of time when an elastic structure is displaced from the rest position and then released. So for the damping, this is the loss of energy when a system is displaced, released, and allowed to undergo free vibration or vibration in the absence of applied forces, which can result in the decrease of vibratory energy over time. So mode shape. So mode shape, this is the spatial pattern when a structural vibrating at a natural frequency or in a mode moves with a characteristic spatial pattern with every point on the structure moving at the same frequency. So how about the modal mass? So modal mass is the part of the total mass that participate in the modal motion. So here, resonance. This resonance is actually most of us don't want to happen into our structure. So this resonance is the condition in which the frequency associated with a continuous force, for instance, walking, matches a natural frequency of a structure. At this state, a structure generally is subjected to vibration that are more severe than those that at not matching at non-matching frequencies. So time history analysis. So this is the analysis step that we are doing for today. So it is also known as nonlinear dynamic analysis. It is an important technique for structural seismic analysis, especially when the evaluated structural response is important. Also, this is a step-by-step analysis of the dynamic response of a structure to a specified loading that may vary with time. So for the dynamic forces, so these dynamic forces is caused, for example, when a human walk, run, bounce, sway, or jump. Inertia forces cause dynamic loads. So an example of this is when a human walk on the ground with his weight. So when his heels strike, there is also a ground reaction for it. And when his knee bends, and when he push up. So this ground reaction with time can be plotted because can be now be plotted. So these are the dynamic loads that is being produced. An example, of course, of vibration caused by pedestrian load. So an example of this is a impulsive force. Sorry. So an impulsive force. When a man walks on the bridge, so let's say the man walks on the bridge and this guy stopped on the center of the bridge and then started to jump. So when he jumped, the first reaction of the bridge is to vibrate downward, go downward, and then it bounce back upward and then downward again. So this cause a vibration, the first mode of vibration. So of course, when this happen, when the beam vibrates, it also create a displacement. So at first impact of the load or the jump, it has carry a large displacement. So as time goes by, those displacement is decreased. So to start the floor vibration analysis and time history plot due to pedestrian load in MIDAS Gen. So we will start with the basic structural modeling. So here in our structural modeling, we can assume that our structure is an 8 by 8 frame. So with a 3 meters column, steel structure, and a concrete slab. So let us start with the modeling. So to start our modeling, so first we can define our properties, material properties. So going to the material properties, we can now click on add. So here for our structural members like the beams and columns, we'll be using a steel section. So let us use ASTM09 with a strength of A36. So clicking on OK. So after we have selected or created the material properties, we can now also define the section properties. So clicking on the add button and selecting AISC10. So let's say we have a column of W10 by 49. Clicking on apply. And the main girder will be, let's say, W14 by 30. Apply. So the last is the intermediate beam. So here in our example, we will also be having an intermediate beam. So let's say we have W12 by 26 as an intermediate beam. Apply. And may I also apply a null section. So why do I have to add a null section? So this null section, I will use this to create a load path for the pedestrian load. So I will just use a very small stiffness. So using 0.001. So clicking on OK. So after we have created the section, we can now also add the thickness for the slab. So I can name it as slab. So after creating the slab, so let's say we have a 125 millimeters thick of slab. So after we have created our section, so we can now start modeling our structure. So there are different ways of modeling here in MIDAS. So to do this, an example that I will use is using a, they call this wizard, structural wizard. So going to the structure tab, base structure, and selecting the frame. So you have to notice that this frame is in XZ coordinate. Here in MIDAS, Z direction is in upward direction. So for the X coordinate, let's say we have a 2-meter distance and the number of repetition or base is 4 meters. So clicking on add X coordinate, and along Y direction, again it is in Z coordinate, but I am stressing that it is in Y direction. So in Y coordinate, let us say we have an 8-meter distance with the number of repetition or bay as 1. So after creating the guide, so we can now go to the edit tab. So I can first generate the frame, and later on I will transfer this XZ plane into XY plane. So first I have to also convert the per specific element into 90 degrees rotation beta angle. So since I will be transferring this XZ plane into XY plane later. So for the material, let us select A36, and for the base section, let us say W14 by 30 as the girder. So after doing that, let us say that the insertion point is 3 meters above the origin, and the rotation alpha, beta, and gamma signify the rotation along X, along Y, and along Z. So if I want to transfer this XZ plane into XY plane, so I will have to rotate this negative 90 degrees. So after doing that, clicking on apply and close, we have created our structural frame, initial structural frame. So going on to the top view, and from the works tab, expanding the section, so I want this portion, these 3 beams, to be assigned as intermediate beam. So since my intermediate beam that I have said before is W12 by 26, I can assign this using select single, selecting all these elements from right to left, and then to assign I can just use drag and drop. So after doing that, we can now also create our column. So going into the isometric view, so in node and element tab, there is an extrude option. So in the extrude option, let us select node to line element since I will be creating a column. The material is A36, the section is W10 by 49. Let us say I want to rotate the columns beta angle into 90 degrees. So selecting first the node where I want to create our column, and then the direction will be -3. Let's say I will generate this into -3 direct along the DZ direction. So after I have created the columns, so it is not clear for us which section is which. So what I will do is go to the display option, then there is a draw tab, and from the element color, so we have this section per thickness color. So I select random color, click on apply, and okay. So same color means same section here in our model. So after we have changed the section and created the column as well, so what we will do next is to add the null section. So the null section, as I have said before, is the direction that I want to do, the direction of the pedestrian load. So to do this, I have to create an element, making sure that the element type is general beam or tapered beam, selecting the section as null, and I can uncheck the node and the element intersect because I want to divide this null element into different length, or this length will represent the stride length of the pedestrian load. So what I will do is to click on nodal connectivity and connect two nodes. So as you can see, I have now created the load path. So this is the direction, for example, of the pedestrian load. So after doing that, let me activate the null element. So going on to the select single, selecting this element, so I can just select active. Going into the top view, so there is a divide option here in MIDAS. So what I will do is use the unequal distance. So this point and this point is actually the point where the column lies. So if I want the pedestrian start 1 meter from this point, so I can just input 1 meter. And for the stride length, as I have said before, let's say we'll do 13 steps. So all in all, we have 12 spaces at 0.75 meter in length. So again, I have to select and apply. So after we have created these loads or these nodes, so we have generated 12 nodes, or I mean 13 nodes. These 13 nodes we will use in the dynamic nodal analysis, or the loads that we will be applying for the time history analysis. So after dividing this element, let me just group this, going to the toggle work tree and group tab. So I can just create a new group, and to assign, just like before, I have to use drag and drop. So 30 nodes have been created. So we will apply nodal loads in these nodes later. So after doing that, we can now view all of the structures. So activate all, going into the isometric view. And after that, we can now intersect the elements. So it is important to always intersect these elements since MIDAS Gen is a finite element software. So selecting, using select single, intersect, and click on apply. So after we have intersected these elements, or all of these elements, so we can now create our slab. So there is an auto-mesh function. So for the method, let us use line element. So the boundaries will be the line element. And for the mesh size, let me use 0.2 for a more accurate result. So let us select the floor which we will be considering in the mesh. So selecting or using the select by plane, going into the XY plane and selecting a node on that plane. So we will mesh this portion. So clicking on close and apply. So as you can see, the slab is now being created. So after we have created the slab, we can now apply the boundary conditions. So going on to the front view, and from the front view, there we have a boundary tab, define support. If I want to make this a fixed support, I want to restrain this into displacement and rotation. So D all represent displacement, R all represent rotation. So I want to restrain this in D all and R all. So selecting the bottom nodes where I want to apply the support, and there you have it. Clicking on apply, the support has been created. So let me just undisplay the nodes. So after we have created the support, let me add also the rigid link. So why do we need to add this rigid link? So first, since we model a steel structure, and the steel structure that we model has a slab, so we want this to the slab to rigidly connect to our columns and the beams. So what we should do is to apply a rigid link using a rigid body. So to apply this, what we should do first is to have a master node. So selecting the master node, we should now select the slave nodes. So as you can see, rigid link is being connected because here in the floor vibration, if we will be considering this, it is very important that the connection of this is rigid, especially when we model the concrete slab with a steel framing. So repeating the same process, so selecting the master node, and then of course the slave nodes. We should do this to the 4 supports. So again, selecting the master node and selecting the slave nodes. Master node and then slave nodes. So after we have applied the boundary condition in our structure, so let us add now the self-weight into mass. So this is actually very important, especially when we are dealing with dynamic analysis. So structure tab, structure type, then convert self-weight into mass. I will just convert it into Z direction because our main concern here is the floor vibration. So we will not be tackling more on the lateral movement of our structure. So convert to Z. After we have convert this into Z, so the next thing that we will do is to add the loadings. So to add the loads, let me first define a static load. So for example, I have a superimposed dead load. Name it as SIDL, and the type is dead load. Close. So after adding the superimposed dead load case, we can now define the pressure load. So there is a pressure load here in MIDAS. So define pressure load type. So let's say we have a finishing load. So selecting the superimposed dead load, and let's say cumulatively, so we have the weight of the ceiling, the drywalls, the the tiles or other superimposed dead load. So cumulatively we have negative 2.54. Let us say we have this pressure load, so we can now click on add. After adding this, We should also add, of course, the self-weight. So self-weight of our structure, -1. So clicking on add. So after adding the self-weight, we can now add also the pressure load. So clicking on pressure load and selecting the load type, we should select the finishing load, the load type name that we have created before. And then for the application of this, let us use the select by plane using XY plane, and let us select a point along the XY plane. So clicking on apply and close. So after doing that, we can now apply the loadings. So after we have applied the loadings, so the next thing that we should do is the loads to masses. So let us check the loads to masses. So again, since we are concerned with the vertical movement of our structure, so we can select the Z direction with a factor of 1 in the superimposed dead load. So there you have it. So after adding these loads, we can now add the analysis. So analysis tab, eigenvalue analysis control. So let us use a number of frequency of 15. So I just added a 15 so that we can see more of the vibration mode shapes to check. So number of frequency is 15, and then we can now click on OK. So after adding the eigenvalue analysis control, we can now perform an initial analysis. After 3.63 seconds, the analysis is completed. So we can now view the results. So results, mode shape, vibration mode shape. We can see, of course, the contour and mode 1. So as you can see, this is the response of our structure based on the acceleration direction that we have selected. So we have created the different modes. So up to 15 modes or mode shapes. So after adding this analysis tab and viewing the graphical result, we should also check for the result in tabular form. So as you can see in the first mode, so this first mode is actually the modes of our structure, or what I mean is the what do you call this, the primary mode of our structure. So as you can see, we have the mode on mode 1, we have a 3.9286 hertz in the frequency, and on the period we have 0.25 by 0.2545. So approximately around 0.1 to 0.5 seconds, the loadings or the period, if we have this period in our structural system, floor structural system, so if we are in the range of 0.1 to 0.5, it is actually, we can call it as, I don't want to use the term safe. We can use, I can use the term within the acceptable limit. So let us take note that the first mode, 3.9286, or the primary mode with a period of 0.2545, and the last mode, 0.0176, or approximately 0.02 in the period. So after doing this, or after viewing the data results or results in table, we can now add the dynamic loads. So let us unlock first and going to the load tab, dynamic loads. First, we can define the time history function. So after add time history function, so here, since we are dealing with the floor vibration, we can consider the heel drop, and there are different heel drop load types. So for this, let us say we have a walking load discontinuous AIJ. So let us use this load type. So for the FS, or the frequency of the load, so this frequency of the load, so here we should input the most unfavorable case for vibration. So here, to do that, the most unfavorable case for vibration is when the integer multiple of the pedestrian frequency, or the frequency of our floor system, coincides with the frequency of the primary mode. So this is because the vibration amplitude by a resonance is increased when the two frequencies match or are at a multiple. So since the frequency of the floor is 3.9286, and we can consider it as approximately 4 Hertz, so in order for resonance to occur, the frequency, or the floor frequency, must be approximately 2 or 4 Hertz. So what we're doing here is that we should simulate or input the time history function in such a way that we will be simulating with the most unfavorable case for vibration. That is when this this resonance may occur. So here, since we have a 3.9286, if we divide it by 2, so we got 1.9643. So why did I divide it by 2? So the normal frequency of pedestrian is ranging at around 1.6 to 2.5 hertz. So in order, if I take a frequency of, let's say, 2 here, so multiplying 2 by 2 is 4. So what do I mean with that? So if I multiply it by 2, means that the frequency match every 2 steps. So I can use either 2 or 4 because the frequency of that steps will coincides. So that's what we are going to do here. So we want the frequency of the load coincides with the frequency of the floor in order to have the most unfavorable condition, which is the resonance to occur. So that's what we are doing here. So that's why I divide the 3.9286 by 2. So to have the what do you call this, the loadings to coincides with the frequency of the load coincides with the floor frequency. So 3.9286 over 2, so 1.9643. So after doing that, so we can now click on OK. So checking in with the results. Mhm. So this is the plot of the response spectrum that we are doing. Sorry, response time history function that for the hill drop that we are doing due to the walking loads. So let me check it again. It continues. So 1.9643. So I forgot the time step. So the time step that we can use here is approximately the 1/10 of the minimum period or the minimum frequency. So since we have spotted or we have checked that the minimum frequency is at a period of 0.017 or approximately 0.02, so we can add the time step as 0.002. So 1/10 of that 0.02. So clicking on OK. So let us remember that the period of the load is 0.508. So we'll use this later. So after doing that, so we can now check, or after that we can now click on apply and cancel. So closing this, after adding the function, of course we should add the load case. So clicking on load case, check the eigenvalue analysis control. So we have number of frequency of 15, and we can now add the load case. So for the load case name, so let us say we have a pedestrian load. So for the pedestrian load, the time history type is transient, as we all know. And for the end time, so the end time to consider the vibration to the final loading input, it should be longer than the needed time. So since we have 13 nodes, as you have, if you remember, we have 13 nodes where we will be applying the nodal loads or dynamic nodal loads. So multiplying it into 0.508. So 0.508 is the period of the loads. So you will have 6.04. So to reflect or to consider the vibration due to the final loading, I should have an end time longer than 6.604 seconds. So that means, let's say, 8 seconds. And for the time increment, so I can use again 0.002. And for the step number increment for output, let us say 1. And for the damping method, let us use modal. And for the damping ratio for all modes, let us say we will be using 0.05. So after doing that, we can now click on OK and close. So after we have added the time history analysis data, so what we will do next is to add the dynamic nodal loads. So first, let me activate the group that I have created before. So double clicking on it, right click, and then active. So let us view or display the nodes and the node number. So 15 to 27. So activating this, we can now add the dynamic nodal loads. So how do we add the dynamic nodal loads? So clicking on dynamic nodal loads, selecting the pedestrian load, the time history load case name that we have added, and for the function name, we can use the walk discontinuous AIJ that we have created before, and the direction of the force will be in Z. So for the arrival time, so since it will start at this point, so it should start at 0. For the scale factor, let us use -1. So let us say the weight of the pedestrian walking is 734 newtons. So for the weight, let us use 1.4 times the weight of the pedestrian. So 1.4 times the weight of the pedestrian is approximately 1 kilonewton. So for the scale factor, let us use -1. So it will be going downward. So click on apply. Sorry. Select the node first, apply. So after doing that, selecting the next node, and the arrival time now is 0.508, the period of the load that we have gathered based on the previous analysis. 0.508 -1, apply. The next one is 0.508 plus 0.508 is 1.016, apply. So to do this, you can use the load table easily. So 15 to 27. So dynamic nodal loads. I can just simply copy it, going to the Excel file. So I can just paste it here. So up to 27, selecting this again. And same value. So what I will do here is just copy, going back to the model and paste. So 15, 16 up to 27, I have easily created the dynamic nodal loads. So after adding these dynamic nodal loads, let me view all first the structure and check the node numbers and the nodes. And the dynamic nodal loads is being created. We can now perform an analysis. So going again to analysis tab, perform analysis. So since we are doing a time history analysis, actually time history analysis is when you perform this type of analysis, it requires more time. So as you can see, we have successfully completed the analysis as at 35.73 seconds. So after performing the analysis, we can again view the mode shapes, different mode shapes. So if you want, you can also check these different mode shapes. So this is actually the response based on the analysis that we have performed. So after performing this analysis, we can now view or plot the graph or text. So to do this, what I will do is to go to time history graph or text, then time history text. So I will just check where is the maximum displacement in my structure. So time history text, I can select displacement. For the output type selection, I can select maximum and minimum. And for the output time, so this is the same for the reference. And for the time history case, so for the node selection, we will use the selected nodes on view. So going into the top view, selecting different nodes. So the program will automatically view the different maximum and minimum of this displacement since we have selected the displacement. So we can now click on apply. So but I will not do this here in our webinar. That's why I have prepared uh, same model. So after we have created, after we have applied, it will now calculate for the maximum and minimum. So since if we perform this, it will take a long time since we have lots of, approximately it is around 2000 nodes. So the time it takes to perform or to plot the different result will take a longer time. So let us view the different results. So for example, this displacement of nodes. So after performing such analysis, you can now view the time history output data. So for the displacement, maximum displacement, to get the maximum displacement in the structure, we can see that at node 360 it is maximum and minimum at node 29. So let us check where is this node 360. So usually the maximum deflection is on the center of the structure. Sorry. Mhm. Node 360. So as you can see, the node 360 is on the center of the structure, and the node 29, so approximately it is also on the, it is near each other. So node 29 as well as node 360, yeah, it is near each other. So after viewing the displacement, maximum displacement, so we can now check also the acceleration. So result type, acceleration, maximum and minimum, and then going on with the same process. So we can now check the acceleration. So this is the output of the software after performing the or viewing the different results based on the selected nodes. So as you can see, it is maximum at node 29. So maximum acceleration at node 29 and minimum at node 1903. So it has this maximum value of acceleration at time 3.132 seconds. So aside from viewing it in data form, we can also view it into graphical form. So to view this into graphical form, so going again to time history graph and then selecting the time history graph, we can now first define the section function. So for this define function, let us select displacement, velocity, and acceleration. So we can add new function. So for this, let us name as displacement maximum. So for the maximum displacement, it is 360 at node 360. So for the type of result, we want to view the displacement. And for the component, of course, we will be dealing with DZ. So include mode number. So all of the modes will be considered. So I can now click on apply. So after that, I can also check for the ground acceleration. I mean the acceleration of the floor system. So let's say acceleration max. So for the maximum acceleration, so maximum acceleration, maximum acceleration. Let me check. Sorry, the graph, the data. So for the maximum acceleration, it is on the node 29. Node 29 acceleration component is along DZ. So I can now click on OK. So as you can see, we have created these two functions. So after doing that, we can now view the graphs. So let us check first the acceleration maximum. So add from list, the horizontal axis will be the time. So let us make this 0 the axis decimal point and changing this into millimeter. So clicking on graph, and if I want to view the time frequency, and also we can check a portion of that structure or that function, frequency and that function. So aside from it is actually maximum acceleration is being reflected, and aside from that we can also add the displacement. So for the displacement, add from list, so same process. So it actually has a maximum acceleration at time 3.78 with an acceleration of this value. So this means when you start to walk, so the maximum displacement occurs at time 3.78 seconds, but the minimum displacement occurs at 3.65 when he started to walk from the load path that we have created. So that concludes my presentation, and if you have other further questions or concern, you can write us back at phinquiry@midasit.com. So for further questions or concerns, you can email us at phinquiry@midasit.com. Hope you enjoy watching this webinar, and if you want to get a free trial, you can just contact us so that we can send you a free evaluation license. So, and regarding trainings, so we can also provide trainings for those who are, especially for those who are actually interested in having their own Midas Gen license. So this concludes all of this. Thank you, and God bless us all.